Hello and welcome back to Calculus 1, section 4.6 on linearization and differentials. It's a two-part lesson where we learn to approximate, so linearization approximates values, differentials approximate change. These are not same concepts. They could be used to calculate same things, but they do it very differently, and fundamentally they are different things. So they are both approximating, but they are approximating, as you can see, different things. So linearization first, and I'll put in parentheses tangent line.
How does this relate to the tangent line?
So in today's day and age, this is something that it's mostly useless to all of you, because you have calculators, computers, access to technology that can compute quickly. The memories and the computing capabilities of your phone are far bigger and larger than all of the NASA's combined computing, when they put someone on the moon. So think about that. Now, what we have is a method to pretty much calculate anything while approximating anything that we actually don't want to calculate. I'm not sure if you ever wondered how they computed square root of 15.2 50 years ago. Just 50 years ago. You don't have to go 500 years ago, right? If you were able to calculate the square root of 15.2 or 500 years ago, they kill you. He knew too much, right? But just 50 years ago, no calculators, no computers. How do you get that? What's the square root of 93.4? What's ln of 4? What's ln of 7.9? How do you calculate those values? What's sine of 12 degrees? Or what's sine of 48 degrees? Yeah, you know sine of 45 degrees. You learned that in school. Root 2 over 2. Great, right? You can do that. But what's the value for root 2? Right? You want to come up with some precise decimals. So see, linearization is going to help us to manually, without calculator, compute these values, whether they're square roots or ln's or whatever you can come up with. So they help you compute the things you don't want to compute without a calculator, right? So to motivate you, let me paint a picture, right? You bought this wonderful, wonderful vacation package. It's a cruise that's going to go to many islands. And as it happens, the ship wrecks, everyone dies, you're the sole survivor. You end up on this desert island, right? You need to build a shelter. To do that, you clearly have to compute the square root of 15.2. It came up, right? You have no cell phone, no calculator, no one to talk to, right? Luckily, you went to the calculus class and you remember linearization, so you can calculate this thing, right? So that's the scenario. So now what we are going to do here is first we are going to understand the concept, hopefully. If I draw square root of x function, and I pick, let's say over here is 15.2 value that I want to compute. And you really don't want to do it, right? What you can do instead is go to the closest value that can be computed nicely without calculator, and that would be 16, right? Yes, you can take a square root of 9 and square root of 100 and square root of 36, but 16 is the closest value that you can take a square root of without the calculator. So you will go to 16 instead, and you will calculate the tangent line at x equals 16. Now what's going to do that to our picture? It's going to come up with this point there, and you will draw the tangent line there, and then when you come up with your 15.2, look at this. Do you see that the value, the blue dot, the value that is the exact value that you would get, well, you don't get exact, you get the decimals, but whatever. And if you calculate 15.2 in a tangent line, they're really close, right? If I zoom out, you can't even tell the difference between the 2 points. See that? Zoom in, yeah, you see they're not the same value. So this is what the linearization or the approximation with the tangent line is all about. Your job, right, your job is to not compute 15.2 in a square root. Your job is to find the tangent line at the point that you can compute in the square root, do the tangent line, and then calculate 15.2 in the tangent line. Because that's just a linear calculation, and that's easy. So, to solve this problem, I am going to say that my function f of x is square root of x, and the number a that I am linearizing at is 16. So you find the tangent line at 16. Now you know the process for tangent line. That's nothing new there, right? You find the derivative, you find the slope, you find b, you're done. So to find the slope, we find the derivative, 1 over 2 root x, and then the slope is that derivative computed at 16, which is 1 over 2 root 16, which is 1 over 8. And we found the slope. Now we find the y value, which is f of 16, which is square root of 16, which is 4. And now I have all the specs I need. I have m equals 1 over 8, and I have my 16,4 point. Y equal mx plus b, and y is 4, m is 1 over 8, x is 16, plus b, so b is 2, exactly. B is 2. So now I have my tangent line. Y equals x over 8 plus 2. That's the tangent line at x equals 16. So now, this is the important part, guys. Square root of 15.2 is approximately close by. So you have a squiggly equal sign. It's not equal, it's squiggly equal. That's the sign for approximate. Square root of 15.2 is given, it's approximated by the tangent line calculated at 15.2, which is 15.2 over 8 plus 2. So now you take the stick, you go on a sand, right? If Wilson is still roaming around kicking an ocean, no help. 15.2 divided by 8 plus 2, 3.9. So now I just want to compare that really quick. Check. Calculator, square root of 15.2. So square root of 15.2, calculator gives me 3.8987. Decimals go forever.
Pretty close.
Yeah. We haven't used any technology to compute that value, right? And we are almost dead on. Do you see that? So next time when someone tells you, what do you know? I can compute the square root of 17.1. What do you know? Right?
Well, they know that as well.
It's a good. Let's see another example because we can. Do what?
Never mind. It's a stupid question. Let's continue, please. I'm excited for it.
Good, because the next one is ln of 3. How much is ln of 3? Yeah, no calculators.
So what was ln again? That's the
Log base c.
That's the log of the base of c.
So how much is this, right?
Will give us which value of e would give us what the base.
What power of e will give you 3? Yes, exactly. So now you're looking at this and you said, I need to find the tangent line, and then I will compute 3 in the tangent line, and those values will be close. So, which value that's close to 3 works nicely with ln? E. Excellent. E is about 2.7. So we will find the tangent line at x equals E. Great. Let's go. First derivative, we all know how this goes. First derivative of ln x is 1 over x. So slope is the first derivative computed at the point. So 1 over e. We have the slope is 1 over e. The y is the function computed at e. And that's ln e. And that's 1. So we have a point e comma 1. Y equal mx plus b. So y is 1, m is 1 over e, x is e plus b, e is cancelled, b 0. So the tangent line is given by y equals x over e. Right, your slope is 1 over e, so slope times m times x. So that's 1 over e times x, which is x over e. So that's your tangent line. So now your ln 3 is approximately equal to 3 divided by e. In this case, we have no b, so it looks weird, but that's what it is. So now you're going to say e is 2.7 as instructed. So we have 3 divided by 2.7. That's 30 over 27 to kill the decimal. Divide by 3 to get 10 over 9, which gives you about 1.111111 forever. So we approximated, without use of any calculators, computers, anything, that ln3 is about 1.11. And now I'm going to go to ln3 in a calculator. ln3 is approximately 1.0986. Oh, come on, we're like 1 cent off when you round it, right?
Yeah, close.
So these methods are awesome. When do these methods fail? They fail when you choose the wrong point. Can you calculate or approximate square root of 16.7 using a square root of 100? No, right? Because the tangent line is going to diverge from the function value. You see, if I go back to the previous graph, this is terrible at 1, right? Because if I want to approximate, let's say 1.3, square root of 1.3, and I use 16, the approximation value is going to give me that as a y value, and the original value is here. So that's going to be a lot of error. Does that make sense? So your job is to find the closest possible point that you can calculate without the calculator and get the tangent line there. Because as you can see in the neighborhood over here, right, in the neighborhood, everything is good. Close. Some of you noble souls are taking and liking physics, right? And in physics, they say your nonlinear equation sine x can be approximated by x for small angles. And then they just replace sine x with x, and you go on computing. A lot of students don't even question it. Oh, another thing I have to memorize. But why small angles? Can I just replace it and be done? Well, they want to approximate sine x by x for small angles.
Okay, you have to be bigger or smaller than 1 and -1, right?
That's the range of sine, but it's not relevant to what we're looking at. So now you have your sine function, which is an infinite wave that does this. And that's your sine x. So now if you call that 2 pi, call that pi, call that 0, pi is 180 degrees. And then with the peak is the pi over 2, which is 90 degrees. If I am to draw function x, which is red, you see that the black and the red line match and go together around 0. Do we all see that?
Yeah.
Yeah, right? We see that. Now around 0 are angles that are small. As soon as you get to pi over 4, which is 45 degrees, the y values, as you can see, are already apart. So when you run into physics, right, your professor says, we are going to approximate sine x with x for small angles. Yeah, it's going to work for, 11 degrees and 15 degrees and 20 degrees, maybe 30 degrees, okay. But it's not going to work for angles bigger than 30 because the error is going to be big. So your job is to find the point that it's very easy to compute without a calculator in your whatever function you have, and then sometimes it's given to you, right? Some of the homework examples, they're just going to give you the point, and then you are done. So we have now two things left, right? One is to write down linearization formula, which is the tangent line one-liner. Okay? Linearization formula in parentheses, aka tangent line in one equation, rather than having the full procedure. L of x is equal to f of a plus f prime of a times x minus a. So you know that your tangent lines is y equal mx plus b, right? So this is your y is the L of x actually, and your m is this. Now this form here is actually better understood if we do this. Y is equal to y1 plus mx minus x1. Do you remember this formula in algebra when you had y minus y1 equals to, right? That's exactly what that formula above is. Your y1 is the function computed at a, which is function computed at x1. So x1 is a, and the y is L of x, and then you know that you're computing the slope through the derivative. So it's a one-liner formula for tangent line. If you want to learn the formula. If you know the process for the tangent line, you know the process for the tangent line, right? Now this formula is good to know for those going into Calc 2, because we are going to upgrade this formula many times, infinitely many times if we want, in Calc 2 to get the precision of any kind that we want. You are over here on two terms. There is going to be a second derivative term, and the third derivative term, and the fourth, and the fifth, and the sixth, and to infinity. And you get to chop it off anywhere and say, well, I need this to be exact for the first 6 decimals, and then the rest I don't care about. Then you say, well, I need 3 terms for that, or I need 4 terms for that. So Calc 2 is going to introduce that. So if you're going to Calc 2, you will be using this equation with even more terms added in Calc 2. So you're technically doing yourself a favor now to learn this much, right? And then just keep adding extra terms which are added through a pattern, which is in the next class. For the rest, students that are having this class as a terminal class, meaning no more calculus after this, your procedure for the tangent line is just fine, because this is the tangent line written in one equation, and if you don't want to bother with it, don't. There's no need, right? You can use your tangent line procedure, because look, I gave you 2 examples. Did I use the formula? No, I used the tangent line procedure, right? So it's perfectly fine for you to just use the tangent line procedure and be done with this. So this is the linearization portion of the lecture. Tomorrow we are going to do differentials, and then we'll have L'Hopital rule, We're starting integration after that. 4.9 is integration. We are introducing integration in chapter 4. Now the question is, exam. Yes. Bye.